I'm going to describe a little more detail, in particular about the very recent work that I'm doing at present, but it is related to the same picture or same line of inquiry that I discussed yesterday. So this talk is really about new technique for measuring the Hubble constant, that is the expansion rate of the universe, and how it can inform us about the nature of dark energy. And this is using tools of supernovae, Cepheids, which I'll talk about, and also in particular a new way to measure parallax in the universe. So I'll just give a very brief background, since this is the more technical talk, and presumably you got to see this expanding grid yesterday. But by carefully measuring the expansion of the universe, especially over time, we can learn a lot about the composition of the universe. Now, what we would like to be able to measure is the scale factor. What we call the scale factor is essentially the legend for this grid, how big in actual size one of these squares is, and we would like to see how that scale factor has changed with time. Unfortunately, there are not giant clocks in the universe, unlike the giant arrows that we sometimes see. And so instead of measuring time, which of course relates to time by the speed of light, and instead of measuring the relative size of the universe, we measured the redshift, which records the growth in the grid of space via the increase in the wavelengths of light that we see. And of course, then by looking further out, we are looking into the past, and so we may expect the slope of this line, which indicates the expansion rate of the universe at present, we may expect that slope to change, and by measuring the rate and the changes, we can learn a lot about the dynamics of the universe and the components of the universe which are driving the various episodes of growth and expansion in the universe. Now, it turns out that most of the information that we can get out of measuring the expansion history of the universe comes from the first two derivatives of the scale factor, A dot and A double dot. A dot, normalized, is also known as the Hubble constant, has a long and famous history going back to Edwin Hubble, and by measuring the Hubble constant, we can determine the present expansion rate of the universe. We can get a scale for the size of the universe, and as well as a scale for the age of the universe. And I talked a little bit about that yesterday. Back in the as late as the 1980s and early 90s, we were uncertain about that scale to within a factor of 2. So it could have been that we lived in a big old universe that is now only slowly expanding, or a small, sprightly universe that's young but rapidly expanding at the present time. And so that we can measure just with relatively nearby distance and redshift measurements to see the current expansion rate. The other important number is the next derivative, known as the deceleration parameter. It's basically A double dot, the second time derivative of the scale factor that you saw. In fact, cosmology used to be called the quest for two numbers, because it was really thought by just measuring these two numbers, we would learn most of what we wanted to know about the universe. So the deceleration would essentially tell us what the mass density was of the universe, and if that mass density was sufficient to recollapse the universe at some point in the future. It also was an important piece of evidence to test a new theory in the early 1980s of what happened after the Big Bang, known as inflation. And inflation predicted that the sum of the energy density of the universe should be very close to unity. And so by measuring the deceleration, whether it was a very large deceleration or a very modest deceleration, we could in essence weigh the universe, determine its geometry, figure out if inflation was viable. Now, of course, that story all changed when we saw the universe was not decelerating at all. It was actually accelerating, and this became a more complicated and richer story as we now are trying to understand the nature of this new component of the universe, dark energy, that appears to dominate the energy density of the universe at present, driving it to accelerate. I went over briefly some additional lines of evidence for this, and I'll just review these very quickly, that the first evidence we had for something was up. It was seeing the accelerated expansion from supernovae, a new technique called baryon acoustic oscillations, which attempts to measure the size it uses the typical separations of galaxies as a standard ruler to measure distances in the universe, has also concluded, as of 2011, that the universe is accelerating. The integrated Sachs-Wolf effect, these are photons from the cosmic microwave background which traverse galaxy potentials and gain energy when they fall in those wells, lose energy when they climb back out, but dark energy has the effect during the transit of opening these potentials and reducing the amount of change. This has been seen to high significance. Observations of the cosmic microwave background indicate that the geometry of the universe is very close to flat, very close to Euclidean. So we know the sum of all energy in the universe is close to unity, yet when we attempt to account for just the matter in the universe, which can be done by observations of weak lensing, observations of galaxy clusters and mass-to-light ratios, observations of large-scale structure, or even from the baryon acoustic oscillations themselves, we only get typically 30% of this total. So there's a 70% chunk that is not contained in matter. That's a perfect match to what's doing this and what's doing this. And then we see on the largest scales, the largest clusters have become weaker in their ability to pull new galaxies in because of the effect of dark energy. We've also seen a change in the absolute scale of the universe that indicates the presence of dark energy. So we're quite convinced that dark energy is real. What we're not convinced about is the ultimate explanation. And so I went over these possibilities yesterday, but I'm going to get a little more quantitative. When we try to understand why the universe is accelerating, we write something that looks akin to the Friedmann equation with various sources, and the kind of gravity you get from these sources depends on the equation of state of the material that gravitates, the ratio of the pressure to the energy density. So we can describe any kind of material and its effect on the universe in general relativity by giving its equation of state, whether it's radiation or matter, or even something like a vacuum energy. So that ends up being the first suspect in our quest to understand why the universe is accelerating, that we indeed do have a large vacuum energy, similar to the cosmological constant mathematically, but physically something that Einstein would not have understood, but is more easily understood as a field, a quantum field that is a part of the universe. So I give you as Exhibit A the recently identified Higgs field. So the Higgs field is a field that is a field embedded in space. It's a scalar field that does not seem to have a time component. And this is an example of dark energy. It's not presumably all the dark energy or the dark energy that's accelerating the universe, but it is a dark energy that we now have observational evidence for its existence. And so it would be additional fields like the Higgs whose gravity would be repulsive. And so this is a feature of the shotgun marriage between quantum mechanics and general relativity, one that we don't understand yet, and yet these components together would produce behavior like this. So we would like to understand that, and more specifically, we'd like to measure to high precision whether the equation of state has been -1 for all of time, because then we will know that we're dealing with a vacuum energy, and we could concentrate our efforts there. It could be that this is a dynamical dark energy, a scalar field that is decaying. You could think of this as inflation light, a sort of late descendant of the inflation field that caused the accelerated expansion after the Big Bang. Presumably, we'd be rolling down a very slow potential field, and we'd be dominated right now by the potential energy of that field, but eventually it would decay. So we hope to be able to see, if that were the case, that the equation of state is not -1, or to actually see the decay, to see a change in the equation of state over time or over redshift. It's even possible that the ultimate state to which that field decays is one where the equation of state becomes positive, in which case the universe could still recollapse. And so we would like to find a departure from W is -1 as indication of that, or yet another possibility is physics theories that are overtaken in time usually fail at some regime or some limit that we have never seen or tested before, and it could be the case that general relativity has a scale-dependent limitation. That is, it begins to fail as the scale factor approaches 1, that is, at the present, or on the scale of the whole universe, in which case we could measure the equation of state on different scales. We can measure it on the scale of the whole universe by measuring the expansion rate. That's mostly what I work on and I've been talking about. But we can measure it at smaller scales, on the scale on which structures grow in the universe by the attractive gravity of material. And as I said, dark energy is beginning to have an effect on that in X-ray clusters. And so if we don't get a consistent value for the equation of state, then one could imagine that GR is not the right theory, that there's a scale-dependent error, and that would be a very important discovery. So the bottom line is that one of the few ways we have of trying to answer this riddle, or at least get a good clue, is to measure the equation of state of dark energy, to measure it well, and to measure it over a range in redshift. So there are many ways to do this, and this is not at all meant to be a summary of the ways to measure the equation of state. I'm actually going to talk about a way I think that had been overlooked for a number of years, but actually can be very valuable, and it is actually the Hubble constant itself. The Hubble constant, combined with observations of the cosmic microwave background, give us very powerful constraints on the equation of state of dark energy. This was first pointed out by Wayne Hu in 2005, who made this nice, simple little plot here, where he pointed out if you fix the cosmic microwave background observation, so this is redshift, so way out here at redshift of 1,000, you imagine that they're fixed. And what I mean by fixed is they're observed so well that you have no wiggle room there. And that indeed has come true. With the WMAP satellite and the Planck satellite, we've measured the cosmic microwave background parameters exquisitely well. So if you lock these down and then you look at how the Hubble parameter, the expansion rate fractionally, will change as a function of redshift depending on the value of the equation of state and its derivative, you'll see in some cases some of the largest departures are at present, at redshift 0, and we call the Hubble parameter at redshift 0 the Hubble constant. That is exactly that number that we seek to measure. So it turns out that in the presence of excellent cosmic microwave background data, the uncertainty in the equation of state will go as twice the uncertainty in the Hubble constant. So if you can measure the Hubble constant to 5% today, you've measured the equation of state to 10%, and that's sort of state of the art right now, I would say about 10%. But looking ahead, and this is a review paper I wrote with David Weinberg and a few others to look at future stage experiments of the cosmic microwave background. If we can measure the Hubble constant to 2 or 1% or 0.5%, we continue to get pretty significant improvements in our knowledge of dark energy. In particular, if we are trying to constrain dark energy to be some value and some derivative, then by being able to measure the Hubble constant to about 1%, we can improve what's called the figure of merit. It's the inverse product of the uncertainties on each of these terms by about 40%. If we can do this in multiple ways, then we would actually have a very reliable way to improve knowledge of dark energy. And so we've sort of set for ourselves as a goal in the next decade to try to measure the Hubble constant to 1%. So how do we measure the Hubble constant to 1%? Well, how do we measure it at all? Well, this is the way we used to measure the Hubble constant, which was to build a distance ladder. After all, what you need to do is to measure a distance out to something like 100 megaparsecs. And if you measure the redshift at 100 megaparsecs and the distance at 100 megaparsecs, the ratio of the two is the Hubble constant. But unfortunately, it's not that easy. We can see objects at 100 megaparsecs, but we don't recognize them. We don't know what their intrinsic luminosity is, or their intrinsic size. And so we have to build a ladder starting with nearby common objects whose luminosity or size we do know, do understand, and then transfer that knowledge to an object that is rarer but can be seen further away, and you continuously do that following some path until you reach 100 megaparsecs and you've measured the Hubble constant. The problem is that every time you take a step here, you are propagating some additional error, some systematic error of some sort. And so we realized in the last few years that you need to, if you're going to get to 1%, you really need to build a very simple, clean, and reliable ladder. Now, one important development in this business has been the observation of a supermassive black hole in the center of a nearby galaxy, NGC 4258, which by chance is seen edge on with radio maser features, water masers, orbiting in Keplerian motion around that supermassive black hole. And a couple decades of monitoring those water masers in the radio has given a beautiful Keplerian rotation curve and about a 3% geometric distance to this galaxy. So that's provided sort of a shortcut, if you will, in the distance ladder as you could jump out right here. Another important development in this game has been the use of the Hubble Space Telescope, as I'll talk about, and in a few years, Gaia, a new European satellite, to directly measure the parallax of pulsating stars called Cepheids. So you measure the geometric distance by good old trigonometric parallax, and then Cepheids can be seen using the Hubble Space Telescope in nearby galaxies, which also hosted Type 1a supernovae. And so you could build a pretty simple ladder that is just geometry, Cepheids, supernovae, and do much better that way. So I started a project called the SHOES project in 2005 to try to measure the Hubble constant to sort of percent level precision with a route just like this. So as I said, the idea was to build a very clean and simple ladder, just geometry, Cepheids, and supernovae, some of the objects that we understand the best or have been our most reliable tools for measuring distances, to reduce systematic errors in past measurements by smarter and more optimized data collection. And I'll tell you how we do that in a minute, but there are ways to collect the data since so many steps in this measurement are just differential steps. One can collect the data in a way so that some of the leading systematic errors of the past drop out. And then to do a very good job of keeping track of the statistical and systematic errors, so at the end you actually really have confidence in the result. So I will talk about these today. First, let me talk a little bit about collecting better data. Type 1a supernovae are still relatively rare, and so in the past, when astronomers would attempt to calibrate their luminosity using an earlier step in the distance ladder, they had to rely on only the nearest Type 1a supernovae, and the nearest ones are incredibly rare, and so they were forced to calibrate objects which had been first observed 70 or 80 years ago. Now we're long faded, and so were only observed on these old Kodak photographic emulsions, which nobody quite remembers or is sure what the part of the spectrum that photographic emulsion contained, and then the photographic emulsions decay over time, so you can't really get the measurements back out. They're not digital, and so there are a lot of problems with some of the old data. So we began to collect and calibrate only modern Type 1a supernovae. So the problem originated with the fact that when Hubble was first built, it had a camera, Wide Field Camera 2, which still was an early generation CCD, and so it could not see out very far and observe Cepheids out beyond about 20 megaparsecs. And in the volume within 20 megaparsecs, there's only a Type 1a supernova about once or twice a decade. And so as a result, as I said, astronomers had to calibrate even things as far back as 1895, 1937, 1960 F. And these events were poorly observed. Astronomy was not in the current state of precision that it is today. So measurements were very noisy. Here's the peak brightness of the supernova varying all over the place. Sometimes the maximum was missed, or they were seen through large clouds of dust, which made it very difficult to estimate the distance. So we began to collect new, modern Type 1a supernovae, aided largely by the astronauts installing two cameras in Hubble. In 2002, they installed the advanced camera. In 2009, they installed the Wide Field Camera 3. These extended the visible range of Hubble for seeing pulsating stars, Cepheids, to about 35 megaparsecs. So that's 8 times the volume. So that means that there's a good Type 1a supernova within range of Hubble now every 1 or 2 years. And so we were able to begin calibrating only objects that were well observed, modern digital data from charged couple devices, caught before maximum, observed in many different filters at a time with low extinction, and the brightness of the Cepheids, of the supernovae, measured with the same tools used to measure the supernovae further out, the ones actually in the expanding universe part. And so that's important for removing systematic errors. As I alluded to before, another important development has been the availability of high-precision geometric first step on the distance ladder, either in the form of this Maser-Hose NGC 4258 or first efforts to measure parallaxes of Cepheids in the Milky Way. There's a couple of papers you could take a look at, but either of these gives you a first step on the distance ladder. That's good to about 3%. And also, very important, you can observe the Cepheids in this galaxy, this Maser galaxy, with the Hubble Space Telescope, and then observe other Cepheids in supernova hosts. And because you're observing both sets of Cepheids with the same telescope, uncertainties about what we call 0 points, or the flux calibration, actually drop out of the analysis. That's a very important aspect of this. Another important improvement we made in the measurement was to make sure that we were observing Cepheids which had the same range in periods. See, Cepheids are pulsating stars, and they pulsate at different periods. The period is tightly correlated to the luminosity. It's easy to understand from basic physics. It just has to do with the mean density of the star and the free fall time. And so because though the actual period luminosity relationship is empirically known and has some uncertainty, you want to observe Cepheids that are all very homogeneous, have very similar periods and similar chemical composition, so that you can use the relative brightness of the Cepheids to indicate the relative distance. And so we were able to do that with Hubble. So here's the Hubble Space Telescope in cartoon, observing Cepheids in the Anchor galaxy and in the hosts of Type 1a supernovae, chopping back and forth, allowing us to measure the relative distance, only needing to know the relative brightness. And so here are composite light curves of all the Cepheids. As I said, they pulsate. They have a light curve that can span anywhere from a few days to up to maybe 100 days. So by doing that, we were able to reduce some of the largest systematic errors. Like today, in measuring high redshift supernovae, some of the largest systematic errors involve the flux calibration, because the redshift forces you to observe supernovae at different points in the spectrum, and figuring out how many ergs per second you get at one point versus another point is very difficult. Here, you don't have to deal with that problem. It's just comparing brightness at the same wavelength points. Finally, we began making our observations in the near-infrared. In the past, Cepheids were always observed in the optical. Well, in the optical, a lot of the light you see is attenuated or absorbed by dust intervening in the Milky Way or in distant galaxies. The near-infrared can see through that dust. Reduction in absorption is about a factor of 6 in the near-infrared. And Cepheids themselves are just better distance indicators. They are more homogeneous in the near-infrared. And so here's an example of how powerful near-infrared observations, especially from space, are. This galaxy is Andromeda. This is the course, the nearest galaxy, and this is the most famous galaxy in terms of Cepheid observations, because a little less than 100 years ago, Edwin Hubble took this photographic plate of Andromeda with the question on everybody's mind, are these spiral nebulae inside the Milky Way or are they outside the Milky Way? And when he spotted this variable, which was a Cepheid variable, and here it is as seen by the Hubble Space Telescope, he was able to determine the distance to Andromeda to be a megaparsec, well outside the Milky Way, and it was established that spiral nebulae are themselves sisters and brothers of the Milky Way galaxy located far away. So there's a long history of using Cepheids for cosmological measurements. The problem is, if you actually try to measure the brightness of the Cepheids to measure distances, you see this galaxy is inclined, and so in an actual image, you see the stars are very much crowded together. This is even as seen by the Hubble Space Telescope, but if you're trying to measure the brightness of this Cepheid, it's going to be impossible not to include a lot of light from the nearby stars, especially if you observe from the ground where the image would be blurred out to, let's see, this is 5 arc seconds, to at least an arc second or two. There'd be no way to separate the light of those stars. So this is the best Cepheid period luminosity relationship. Here's log period and here's luminosity, as observed from the ground in the optical. And then this is something I did about 2 years ago, was collect observations of these Cepheids with the Hubble Space Telescope in the near infrared. And you could see what a tight relationship this is if you're able to avoid the contaminating light of other stars, and you're able to see through the dust that would affect you in these galaxies. So near infrared observations from space are very powerful for measuring distances. So in the end, we built a distance ladder that just involved 3 easy steps, I would say. You could start out with either NGC 4258 as the anchor or these Milky Way parallaxes, and then you have a Cepheid bridge that takes you from there to a bunch of galaxies at sort of 20 to 30 megaparsecs, which hosted recent Type 1a supernovae, and you use the period luminosity relationships you see in each of these to tell you the relative distance. Now you've calibrated the supernovae, and now you build a supernova bridge into the Hubble flow. And so here is the distance in astronomer units, and this is the log redshift, and so this straight line here measures the expansion rate of the universe once you have calibrated these supernovae. And so in the end, we got a Hubble constant of 73.8 plus or minus 2.4, so this is good to about 3.5%, and as I'll show in a minute, combined with WMAP already gives you a measurement of the equation of state, which is pretty state-of-the-art. Minus 1.08 plus or minus 0.10 is about as well as any other measurements have determined the equation of state at present. In terms of systematics, by carefully designing how we took the data, we were really able to reduce our systematics. So what I show here are, well, this is the Hubble constant, and here are 15 plausible variants, different ways of doing the analysis, different assumptions that people might have made in the literature or that are sometimes debated, different ways to analyze Cepheids, different ways to analyze supernovae, or even different anchors to use for the first step. And what we found was that the variance is still quite a bit smaller from these systematics than just our statistical uncertainty. That is, it's sort of a 3.2% statistical uncertainty, and you could sort of kick the Hubble constant around by about 1.1% by making different choices in the analysis. So what this showed us is that there's still room for improvement, mostly just by continuing to collect more of this data. Already, as I said, it has a lot of leverage combined with observations from the cosmic microwave background. So these are WMAP 7-year results, the equation of state of dark energy versus the Hubble constant, also the sum of neutrino masses, also the number of neutrino species. Important degeneracy is broken by having knowledge of the Hubble constant. And so these are different stages of measurements. This is what had been done. This is WMAP only, the orange, so very degenerate. This is combining knowledge circa 10 years ago from the Hubble Key project. And then our 2 rounds of making new measurements, SHOES and SHOES 2, that were down to contours like this. And there are important physics questions underlying these. I talked about dark energy and trying to understand whether it's static or variable, but there are still questions about neutrinos, like how much do they weigh, what is the right hierarchy of mass states, and so being able to measure more precisely astrophysically is very important. It actually is one of the best ways that we get constraints on the sum of neutrino masses. Also, there have been questions about whether there's room for a sterile neutrino or not beyond the current known 3. So again, improving these kinds of measurements is very critical. Here is our fairly detailed error budget for measuring the Hubble constant. So this is where it was as measured by the Hubble Key Project circa 2001, and by attacking the various sources of systematic error, we have now gotten down to a total of uncertainty of about 3.3%, and the uncertainty is now fairly well distributed over a number of different sources. What I'm going to tell you about now are the plans we have and projects we're doing right now to try to still double the precision of the measurement of the Hubble constant. And that comes from attacking two of the bigger terms remaining. The first is the anchor, how well we know the distance to that first rung on the ladder. I told you that we know the distance to this special galaxy, NGC 4258, to 3%. So we can't do better than 3% by sticking with that galaxy. We have to move on to parallaxes. Likewise, we need to observe more Type 1a supernovae in this critical intermediate range. Not so far out that we can't see Cepheids in their hosts, but still allow us to calibrate the Type 1a supernovae that are out in the Hubble flow. So I'm going to tell you about two aspects of this work right now. The first we began last year is just to increase the number of Type 1a supernovae in that intermediate range that have been observed both for their supernovae and their Cepheids. So the previous total was about 8, and by the end of next year, we should be up to about 17. So that's a nice square root 2 improvement. And we just began that just last year, and so here is a galaxy that hosted a recent Type 1a supernova, and we've begun observing these pulsating stars using the Hubble Space Telescope, and that seems to be working pretty well, and that's very straightforward. You sort of turn the crank, we know how to do this, nothing too challenging there. The really interesting part, and I'm going to spend the rest of my time talking about this, is a really novel technique to confront a very difficult problem. The problem is, while we would like to measure the trigonometric parallax of Cepheid variables in the Milky Way, they're just too darn far away to measure that. The angles involved become very small. And in particular, it's the longest period Cepheids, the ones that are rarest, but the most luminous, that are the ones that we so want to calibrate, and they are, of course, the furthest away. But they're very important because those are the only kinds we can see in distant galaxies that host supernovae, simply because they're the most luminous, so they're the easiest to see. And so here is the log period of the Cepheid, and here is its distance. These are, every point here is a known Cepheid in the Milky Way. Now, if you look at the Cepheids we see in supernova hosts, you see that they are all these very long period ones that are very luminous. So, of course, this is like you look in a crowd of people, and the people you could see furthest away are the tallest people, right? And so it's not that there aren't shorter people in the crowd further away, it's just this is all you can see. And likewise, with these Cepheids, we can only see the longest period ones. And yet, the handful that have been calibrated are the short period ones because those are the most common. So we find them in the smaller radius that we can measure parallax. So these were measured by the fine guidance sensor on the Hubble Space Telescope. With the exception of this one, 9 out of the 10 of them are all much shorter period than anything that we see in distant galaxies. We would like to be able to measure the parallax of these Cepheids, the ones that do have long periods that would be good analogs to the distant ones. But the problem is you have to be able to measure the parallax quite significantly with good precision out at something like 2 kiloparsecs away from the sun. So that means we have to go from being able to measure angles to a precision of 400 microarc seconds to get down to a precision of 40 microarc seconds. We need a good order of magnitude improvement in our ability to measure these small parallax angles. How in the world can we do that? Well, let me remind you of how you measure parallax, the sort of Astronomy 101. This is easy to do because I teach Astronomy 101. This is the picture I show in Astronomy 101. Here's a field of stars. This purple one presumably is nearby, and these other ones are presumably much further away. And you take an image, and you wait 6 months, and because the Earth goes around the sun, we change our perspective on this field. And so we can measure the angle through which the purple star has moved, and knowing the baseline, knowing the diameter of Earth's orbit around the sun, simple geometry tells us the distance. Now, what does that translate into for real objects, and let's say the Hubble Space Telescope, which is good at measuring small angles? Well, if we look at the Hubble Space Telescope, we can figure out the position of a star, like this purple star, to a precision of about 1/100th of a pixel. Okay, that's our base uncertainty. And that translates into about 400 micro arc seconds of uncertainty, which translates into about a 2 sigma detection of parallax at 2 kiloparsecs. Well, 2 sigma is not good enough. 2 sigma just tells you, yes, that star is far away. It's not nearby. But we want to really measure this at 20 sigma. We want to be able to measure the distance. And so here's the problem. As I said, here's an image, a CCD image from the Hubble Space Telescope. And here is, let's say, a reference star. And here's, let's say, the nearby star. And you're trying to measure their separation. And you can see you're just limited by the number of pixels involved in the measurement. Even if you know what function, we call the point spread function of the telescope, even if you know what function to fit to this, your precision in centroiding or locating any star here is about 1/100th of a pixel. So the new idea that I came up with about 2 years ago now is, what if you scanned or drift scanned the telescope in the direction perpendicular to the parallax direction? Okay, so whoops. So that would look like this, okay? Same image, except now you've dragged it in this direction. So your goal is to measure the separation between these two lines and then measure it again 6 months later and 6 months later. But you can see it's much easier now because you have so many more pixels involved in the measurement. It's as though you were repeating the measurement with, 1,000 samples. You should easily get an order of magnitude improvement in this. And indeed, that's what we see you do. So here's the first example. We began in October of 2011. Here is the Cepheid star, and here are other stars, many of which are in the background. And the blue square is the footprint of the camera at the start of the exposure, and the purple is the footprint of the camera at the end of the exposure. And so you can see all the points turn into nice parallel lines. And here's the Cepheid, very bright. You can see some stars that I've marked here where they show up. And so your goal is to measure pixel by pixel the separation between these lines in this direction, the direction that's perpendicular to parallax. So you intentionally figure out which axis most of the parallax will be along, and you orient the scan perpendicular to that. Now, this gives you two things that are incredibly valuable. So here I've taken these scan lines now, and I've extracted them pixel by pixel. And so what you see here is this is the direction along the scan, and this is the direction perpendicular to the scan. And I've aligned them in time. And so first you look at this and you think, boy, these look really noisy, these lines. What's all this noise? And then if you look very carefully, you notice, wow, that noise is completely correlated, or very correlated, from scan line to scan line. This is not noise. This is the jitter of the telescope. The telescope is bouncing along a little bit in the direction perpendicular to the scan. And normally, if you're an observer who's just staring at some image, you have to suffer the consequences of this, that every nice tight point source is jiggling, and the image you're getting is the superposition of all the jiggled point sources. Well, we are resolving that jitter, and we are trying to measure the separation between stars pixel by pixel. And so when you take the difference between any pair of lines, then the jitter cancels out. And so what you get is the ability to remove the jitter noise and still to average over thousands of pixels. So there's two big advantages here to scanning: removing the jitter, averaging over thousands of measurements, And there's even one more, which is you can measure the brightness of the Cepheid, which normally is so bright it would saturate your detector, but by scanning, you don't saturate, and you can measure the brightness now with the same instrument you use to measure the very distant Cepheids, again, allowing the 0 points to sort of cancel out. So this shows what kind of astrometric precision we can get in a single exposure. It is a function of how bright the star is, because if the star isn't bright enough, you're just not getting enough photons per pixel to max out the precision of the measurement. But once you get to something like a Cepheid, you definitely are maxing out. So we can get to something like 20 microarcseconds, which is even better than what Gaia will get in a single exposure. Of course, Gaia will be dedicated to doing this for 6 years, so eventually Gaia will get down here. But it's a clean order of magnitude better than what you get just from staring mode observations. And so I began doing this, as I said, about 2 years ago, and so we have now gotten the first set of observations of the first field. And so in each of these, you have to observe at least 3 epochs of 6 months each. The first epoch tells you where the star is. The next epoch gives you parallax, but it also gives you proper motion. The star moves along the sky. It's moving off to some location, we don't know where. But if you wait a year, then the star is returned to where it should be due to parallax, and now you can measure the proper motion part because it's in some other place. And then, of course, you may want to add another observation just to make sure there isn't something else funny going on, like the star is in a binary and there's some other kind of motion. So what you mostly see are these jiggity-jow, or these seesaw curves, because we've subtracted out the proper motion, and so you're just seeing the part due to parallax. So I'll draw your eye to some of them. Here is a star where we have very good signal to noise, and so we're down to 20 microarcsecond uncertainty, and so that is allowing us to measure a parallax out to 8 kiloparsecs. That's good to about 15%. That is, the error in the parallax is about 125 microarcseconds. Here is another star that's very nearby, obviously, because it has huge parallax, 4 milliarcseconds, and we measure that very well to 1.8% uncertainty. So this is a star right in your face at 250 parsecs. And so in a few cases, you'll see I've changed the scale. Then that shows you the nearby stars. And just to compare, for a star like this, here is what the error bar would have looked like from the fine guidance sensor on Hubble, the old best way of measuring parallax. And you can see, you can't even see really our error bars very well. So we're getting much more precise. And of course, here's the real target that we care about. These are all stars in the field of this Cepheid. And here's a Cepheid that is at about 2 kiloparsecs. So we're getting down to about 6% error on this. So, about a 20 sigma detection of its parallax. And just last month, I got a 5th epoch, which I can add to this now. And so you can see, we're very clearly detecting the parallax very well as we see these stars just after proper motion is removed, just wagging back and forth. And it's just, as I said, the amplitude of this that is telling you the distance. So this looks very promising. This is the history of parallax measurements for Cepheids in the Milky Way. And so Hipparcos did this first back around 2000, but had very low precision, could only measure the very nearest Cepheids. And so not only did it get low precision, these are the short period Cepheids that, as I said, are not good analogs for the distant ones that we see in distant galaxies. Here was the best done by the fine guidance sensor on HST, getting out to a few hundred parsecs, a precision of about 8%. Again, short period Cepheids. And with this new technique, this is what we simulate we should be able to get. We are currently measuring 20 Cepheids, and we expect to be able to get to about 6 or 7% uncertainty, but these will be long period Cepheids, so they'll be excellent analogs for the distant ones, and we can measure their photometry at the same time to make them most useful for measuring distances and the Hubble constant. So I would say stay tuned for this, but we think with this technique alone, we could get down to about 1.8% uncertainty. Now, looking ahead, Gaia is due to launch later this year, or maybe it'll slip to the beginning of next year. It has a 5 or 6 year mission to observe the whole sky, and at the end of that mission, it should do even better, much better than we have done, because by observing the whole sky, they will have been able to observe some 200 Cepheids with long periods and very precise parallaxes. And so that, combined with photometry from the Hubble Space Telescope, which we're collecting now, should provide the basis for approaching 1% in the Hubble constant. So this is my previous error budget, but now I've updated various terms due to various planned missions like the Hubble Space Telescope, the James Webb Space Telescope, Gaia, and I think it's quite plausible we could get down to about 1% uncertainty in the Hubble constant. And if there are multiple methods, and I list here, people are trying to use strong lensing, other maser systems, baryon acoustic oscillations to try to measure the Hubble constant more accurately, you might be able to combine a number of these methods to get down to sort of 0.5% uncertainty. So I think the Hubble constant is going to be one of the strong tools in the toolkit of many tools we bring to bear on trying to measure the equation of state of dark energy and its derivative to learn more about the nature of dark energy. So I will end there and take any questions you have. Thanks.
Archie, can you raise the lights in the auditorium, please, Ray? Are there questions? Thank you. Vern.
So actually, could you say once more how you determine the distance to this maser galaxy? That was what did.
Right. So there are these clouds, these clouds, water that maze. They get, I guess, pumped up from background radiation from the black hole and its accretion disk. And so they monitor these over a couple of decades, and they measure their proper motion, they measure their centripetal acceleration, and combining those, they're able to determine the geometric distance, the radius of these, and by comparing that to the visual radius, then they get the actual distance, and this distance is good to about 3%. Sure. I mean, we're not sure if there is a multiverse, if there are other universes, but I expect from what we understand of the Big Bang and inflation that this would be a fairly generic property of any universe. The Hubble constant of another universe could be a negative number, it could be contracting, it could be a positive number, it could be expanding. I'd love to know how other creatures in other universes are measuring their expansion rate. But yeah, I think it's... No, we can't. But it does seem to be it is probably a generic property of a universe.
Yes.
I had actually two questions. So one of your earlier slides, you had 3 possibilities for explanation. And the second one was like this transient dark energy that's sort of like, is there and then decays. So I have a hard time. I understand that you can nail the constant down at -1 or absent, but I have a hard time understanding how you ever attempt to measure something like this that plays out over longer than we live, or the civilization lives. How do you actually go about nailing this down?
Well, you look in the past. You look at high redshifts, and you would measure the equation of state at redshift 1 or redshift 2, redshift 1/2, and do it to enough precision and see that it's changing between the past and the present. That is, you would have to see that there's a departure from -1 somewhere, or have enough measurements with enough precision to say that there's a slope to it. Now, it is possible, this has been pointed out many times in the literature, that you could have a decaying scalar field that is decaying so slowly that it looks like -1 at all redshifts. And so that's why most of us in the field consider, the most exciting thing you could observe is to rule out -1, to find a derivative, because that would definitely tell you something. That would tell you that it's not the cosmological constant. But you could make measurements that are consistent with the cosmological constant and yet never rule out the other possibility.
My
Yeah.
The second one, I mean, like, okay, so now coming back to the Hubble, you showed these noise, what you said, first called nose lines, and then there were a couple of these jerks in there. I mean, is it known why this happens? I mean, they're doing something to the instrument?
Yeah, I think it's one of two things, and it may depend on which event you're looking at. I think, let's see, let me go back to, yeah, so I see these. They're sporadic. Some scans will have multiple, and some will have none. So like this spike and this spike. So one thought is these could be little micrometeorites pinging the telescope, and so the whole thing gets a kind of a jerk. But of course, it's a rigid telescope, so it happens to everything on it. If I really cared, I guess I would probably look and try to find out what the other instruments are seeing at that time. Another possibility is it's the control law. So it's the control law of the telescope. It's locked on some guide star, moving that guide star along, and it suddenly notices that it's falling out of the aperture, and it makes a correction, and that correction is, a kind of a jerk. So I don't know which of those it is. For the purpose of this measurement, it never mattered because, as I said, we subtract them. Although they're impressive in that they are clearly a kind of jitter that is not part of the power spectrum of the rest of the fluctuations. Morgan. Sorry, say again? Yes. Yeah, so GaiaLAX is a parallax measuring machine. It is a large array of CCDs where the sky drifts across it, and it measures to very high precision. Actually, a lot of ways very analogous to what we're doing with this scanning. It's making many repeated observations to lock down the positions, and then it's doing it over the whole sky. So at the end of the day, it will get very precise parallaxes. What it won't get is the brightness measurements on the same system as we do for extragalactic Cepheids.
Dan?
You showed a plot of some global fits earlier, among others, the likely number of neutrino species. That used WMAP data.
Correct.
Does it improve in precision with flight data?
I believe it does. It's interesting. It improves in precision, and yet other tensions arise. There's been a fair bit of discussion of tension between the Hubble constant that you would infer from Planck versus what you would infer from WMAP versus what you actually measure locally. And right now, that tension is sort of 2.5, 3 sigma. And so this is exactly the reason we're trying to make these measurements, because by tension, what I really mean to say is if you insist that dark energy is the cosmological constant, that the equation of state has always been -1, and you take that assumption and you use it to extrapolate from shortly after the Big Bang, when you see the cosmic microwave background radiation, to today, then you get a Hubble constant that's a little bit smaller than what we observe. So what does that mean? Well, it either means that the Planck people have made a mistake, we've made a mistake, or more exciting, that dark energy is stronger today. The equation of state is less than -1. That's exactly why we're doing this experiment, is to learn about dark energy, to see whether the Hubble constant you measured today is what you would have expected with the simplest explanation of dark energy and the measurements of the cosmic microwave background. Mm-hmm. Mm-hmm. Right. So that error has come down some with this Planck data, and the Planck data combined with these other observables is closer to 3 now. And so the community was sort of a Twitter a couple of years ago based on this WMAP data that, there was 2 sigma evidence for another species, but that seems to have dropped. So I would say it's been less interesting.
What are you expecting from the Webb telescope?
Yeah, well, hopefully the Webb telescope has the image quality to allow, what you really get out of telescopes like that are kind of resolution that we don't get from the ground. And so when I talk about observing Cepheid stars, you're talking about looking at a galaxy that has 100 billion stars and being able to resolve an individual star in that galaxy. And so the James Webb Space Telescope may allow us to do that even further out. And I've done some calculations. If we can do it as far as expected, we will be able to calibrate many more supernovae, and I can get that term, which is one of the leading terms in the error budget, down to about 0.5%. And so, it's not crazy in that era to start talking about measuring the Hubble constant to 0.5%. And every factor of 2 really makes a difference at this point. I mean, we're trying to see if we can break general relativity or break lambda, and if it is going to be broken, there's no reason to expect any particular scale on which it's broken, which means every factor of 2 sort of gives you a 50% chance, if you're agnostic, of making an amazing discovery.
One more question, yes?
The image of the Cepheid in a nearby galaxy looked like a very crowded field, and I would expect that most of the stars in that field were in that same galaxy, would have the same parallax. How do you choose what to reference your Cepheid motion relative to?
So when I showed pictures of stars in Andromeda, Andromeda is so far away that we cannot measure parallax to it. And so all the parallax measurements are of stars in the Milky Way itself, with some stars being nearby, some stars being very far away. When we start looking at other galaxies like Andromeda, at that point we have calibrated the luminosity of a Cepheid using the nearby ones and parallax measurements, and then that's purely photometric. We're just using the brightness of the Cepheid to tell us its distance. But still, the crowding is a problem with all the other stars, but when you have the resolution of HST, you could see the other stars, and then you simultaneously fit the scene as the superposition of a bright star in the center and a bunch of other stars, and by varying the amplitudes of those, you get a good, in a chi-square sense, fit to the scene and a good measure of the brightness of the Cepheid.
Let's thank our speaker again.